How can changing coordinate systems simplify problems? We've seen a great example from polar coordinates where we can use r and theta to describe points in the xy plane, and this makes it much easier for us to write regions of integration that are circular. They're much more straightforward to describe using our r theta coordinate system, where they might have constant bounds, than they would be in our xy coordinate system directly, because in rectangular the bounds would have to be functions. As an example of a different type of coordinates, consider a pretty simple region in the xy plane. It's just a rectangle and it's going out to A and up to B. Now, we can actually, it's not obvious why we would want to simplify this, but this example will help us think about harder ones. We could actually come up with new coordinates where the bounds 1 in one of the coordinates corresponds to this point A. So I want this point at 1, 0 in the parameter coordinates to correspond to the point A, 0 over in real space. And I want the point 0, 1 to correspond to the point 0, B back in real space. And so now, under this coordinate transformation, this rectangle over here becomes a square in our parameter coordinates. And so what transformation does that? Let x equal AS and y equal BT. When s is 0, x is 0. And when s is 1, x is A. When t is 0, y is 0. And when t is 1, y is B. So these parameter coordinates, x goes from 0 to A, while s goes from 0 to 1. Y goes from 0 to B, while t goes from 0 to 1. So these coordinates transform this rectangle into a square back in ST space. What if we wanted to set up an integral over the rectangular region in the xy plane of a function f of x, y, dA, where we're thinking of dA as dx, dy, but instead we want to write this using our s and t coordinates. So our function needs to be f of as, bt, to change the variables within the function. And dA is going to become some factor times ds dt. And of course the bounds are quite easy because we know that this is a unit square, if this is our region R, back in the ST space. And so the big question is, what is the number or factor that goes here as part of the area element? Why is there a number as part of the area element? Because the area of a box of sides ds dt back in ST space has a different area in xy space, and we want to figure out what its area is in xy space to add this information up. To deal with the area element in the integral, we create a little box of sides delta s, delta t, and we ask how large a corresponding box is in our xy space. And so if s changes by delta s, we get some vector that occurs in xy space corresponding to a change in delta s, and this is delta s times the rate of change of the x-coordinate with respect to s in the I direction, plus the rate of change of the y-coordinate with respect to s in the j direction. So this creates a vector expressing how approximately how much, so the change in s times its rate of change is an approximation of the change in x, and the change in s times its the rate of change of y is an approximation of the change in y. So this vector approximates how x changes and how y changes with a change in s of delta s. And we can find a similar vector for a change of delta t, and so that will be delta t times the rate of change of the x-coordinate with respect to ti, plus the rate of change of the y-coordinate with respect to tj. And if you recall from polar, the way that we found this the area of this box was to take the cross product of these two vectors. Specifically, the area element of this new box over here will be the magnitude of the cross product, and that is the change in S times the change in T times the magnitude of the rate of change of X with respect to S, I, plus the rate of change of Y with respect to S, J, crossed with the rate of change of X with respect to T, I, plus the rate of change of Y with respect to T, J. So these two vectors, this vector gives us one edge of this box, this vector gives us a different edge of this box. The magnitude of their cross product is delta A, the area of this box, and of course then we'll take the limit as delta S and delta T go to 0 to get dA. And so what is this cross product? Well, actually we can do it quite generally because there are no k components around, and this x sub si cross x sub ti, that's going to be 0, y sub sj cross y sub tj, that's going to be 0. So although there are 4 terms to this cross product, 2 of them are 0, and so we're left with just 2 terms, and we can write that out quite generally. This is delta s, delta t. So y sub s, x sub t, j cross I, which is negative k, plus x sub s plus x sub s cross y sub t, x sub si cross y sub tj, and that is x sub s y sub t, I cross j, which is k. And so this is equal to delta s, delta t, the absolute value of x sub s y sub t minus x sub t y sub s. Of course, that was times k, but the magnitude of the k vector was just 1. And so this is quite general. Quite generally, delta A equals, we can actually write this in a shorthand notation as a determinant. It equals the magnitude of the determinant. X sub s goes there, y sub t goes there, x sub t goes there, y sub s goes there, delta s, delta t. So this determinant becomes x sub s times y sub t minus x sub t times y sub s. It's exactly the quantity we got there, and we do want the absolute value. And so this is a general expression. We haven't used yet our information about our particular coordinate system. We can go ahead and substitute that in to figure out delta A. For our particular coordinate system, x sub s is A, x sub t is 0, y sub s is 0, and y sub t is b. And so for our new coordinates, dA is equal to AB ds dt. And so now as we go to set up our integral, to integrate over this rectangular region in the xy plane, we send s from 0 to 1, we send t from 0 to 1, we evaluate our function using the s and t variables, and our dA will be a, b, dt, ds. And so this integral is an integral of a function over this rectangular region re-expressed in our new coordinate system, where instead of being a rectangle, we're now integrating over the unit square. Let's use this exact same idea, but go to a slightly more interesting set of coordinates. So now imagine that we've been given a parallelogram region that we're going to want to integrate over, with its passing through 0, 0. We can use this same idea of trying to transform it to a rectangle in ST space. And so now we would want the point 1, 0 in ST space to correspond to the point 3, 1 in XY space. And so that means that when S equals 1, t equals 0, we want to have x equals 3, y equals 1. And then when we're up at this point, which is s equals 0, t equals 1, we want to have x equals 1, y equals 2. Typically for a coordinate change of this type, very generally, x would be a number, let's say a1, times s plus a2 times t plus a3, some shift, and y would be b1s plus b2t plus some shift, b3. Now in this case, we want 0, 0 when t and s are 0, 0, so these shifts should both be 0. And so given the coordinates that we want, when s is 0, when s is 0, so a1 isn't playing a role, and t is 1, we want x to be 1, so that means a2 should be 1. And when s is 1 and t is 0, we want a 3, so a1 should be 3. When t is 1 and s is 0, we want y to be 2. And finally, when t is 0 and s is 1, we want y to be 1. And so we have a change of coordinates. X equals 3s plus t, y equals s plus 2t. And this change of coordinates means that the range 0, 1, 0, 1, this square in ST space, describes this parallelogram in XY space. And so if we wanted to set up an integral over the parallelogram, the integral over the region of some function f of x comma y dA, we could set this up using our ST coordinates, and it would be the integral from 0 to 1, the integral from 0 to 1, because this unit square in ST corresponds to this parallelogram. Then, of course, we need to transform the function, so f of 3s plus t, comma s plus 2t. And then we need to deal with dA, and we are able to do that via this determinant. So there will be a dA here that needs to be written in our new coordinates. To find dA, we'll take this determinant. X sub s is 3, x sub t is 1, y sub s is 1, y sub t is 2, and so this is 6 minus 1 equals 5. And so we have the integral from 0 to 1, the integral from 0 to 1, the function written in our new variables, 5 ds dt. And so this integral in our new coordinates is describing this parallelogram and a function of points on this parallelogram using new coordinates that simplify it.